So I think we can start the morning session. The first speaker of this morning is Professor Masahide Yamaguchi from the Institute for Basic Science, who is going to talk about cosmological colliders of physics. So please, Masahide, the stage is yours.
Hello. Okay, it works. Okay. First of all, thank you for invitation. I would like to really thank the organizer, especially Luca, for kind invitation. This is my first visit to Campagna, and this is very wonderful workshop and beautiful locations. And second, I would like to thank all of you, your audience. Even though yesterday we had a banquet, normally so first talk the next day, there is almost no audience, but here there are many people than I expected, so thank you so much. And before coming here, I was in Salerno with my wife to visit Professor Gaetano Lambiase, and on Sunday before coming here, I went to Amalfi Coast and bought this shirts with lemon, so it's quite nice. And anyway, yeah, thank you so much. And today I'm going to talk about cosmological collider physics. And this talk is based on the series of collaborations, and these are the good collaborators. And before going to physics, let me introduce our center. 2 years ago, I moved to Korea from Japan to initiate a new center called the IBS CTPU CGA. And now our center is rapidly growing. 2 years ago, just I was alone as a director, but now we have around 20 members. And each winter or each year, we are going to hire 5 or 6 new postdocs. So if you are interested in, please apply for even this winter. And also not only postdocs, but also we accept internship students. 6 months or 1 year, or even like Mikhail, who is another attendant of this workshop and gave a poster presentation on the topological defect. If your advisor agrees, we can accept some PhD student, and I can serve as an effective advisor. So if you are interested, please contact me. And back to physics. Now, this is some schematic figure of the history of the collider on Earth. Okay, so taken from this paper. And unfortunately, energy scale of the collider on Earth is going to saturate. Is it like this one? Lepton collider or even hadron collider. And so, at least in the long span, we need alternative or complementary one. Okay? So what can be the alternative to collider on Earth? So somehow radius of the Earth is limited. So of course you can make a collider outside Earth, and we have another one, you see. Cosmology or universe is somehow natural collider, and will be the unique place for alternative colliders. And in fact, in universe, high energy state is easily excited and realized, or was excited. So in this sense, we have a natural accelerator or collider in the universe. Okay. So generally speaking, there are 2 new ways to probe high energy physics through universe or cosmology. High energy state and new particle are produced in early universe and also astrophysical objects. So in case of cosmological collider, so-called the cosmological collider program, heavy particle can be excited at 3 level or loop level during inflation, and such an excitation can leave imprint on the primordial curvature perturbation. So if we take a look at the primordial curvature perturbation in detail, we can extract the information of such a heavy particle or even the new particle of the beyond the standard model of particle physics from there. And in this talk, we are going to concentrate on this one. And yet another interesting possibility, of course, high energy astrophysics. Particles are accelerated in astrophysical objects. And this is quite a hot topic. But still, acceleration mechanism and origin of the high energy cosmic ray has not yet been well understood. So this is still very interesting. But in this talk, we concentrate on this part. Okay. So important point is this one, quite simple. Any field or particle can be excited during the inflation as a result of quantum fluctuation or classical fluctuation. And this phenomenon is quite similar to the production of the particle by collider on Earth. Okay. So content of my talk is follows. First, I'm going to give a brief introduction what's a cosmological collider and how good it is and how bad it is. And especially, cosmological collider program can probe physics of the Hubble scale during the inflation. But this might not what particle physicists would like to know. When I give a talk on the cosmological collider, some of the particle physicists complain. For example, mass of the new particle during the inflation could be different from the mass in the current universe. And the particle physicists are much more interested in this one. Of course, this is fantastic. So, how to extract current mass of the heavy particle or beyond the standard model of particle physics in the universe through cosmological collider program. This is what I would like to discuss in this talk. And also, maybe I don't have enough time. If I have enough time, I'm going to discuss the coupling of the beyond the standard model in the context of the cosmological collider. But maybe I don't have enough time. And finally, I summarize my talk. And before going to the detail of the cosmological collider, first I'd like to mention how special cosmological collider is for the purpose of the probing the beyond the standard model of the particle physics. Okay? In the standard technique to probe BSL on Earth, if the energy scale of new physics is getting higher and higher, its detection becomes more and more difficult in general, simply because colliders on Earth cannot produce too heavy particles. For example, LHC cannot produce the heavy particle with mass than more than 10 TeV or 100 TeV, simply. Or even in the indirect expression of physics, typically signal gets weaker and weaker as the breaking scale of the new physics gets higher and higher. So typically, the new technique or experiment to probe physics beyond the standard model on Earth, we get lower bound on new physics or new physics breaking scale. This is somehow generic feature. On the other hand, if we go to cosmology, there are several exceptions to this argument. One of the famous examples is the so-called topological effect, especially cosmic strings. Simply because deficit angle and tension are proportional to the breaking scale, exactly speaking, square of the new physics. So the absence of the non-detection of this kind of the strict cosmic strings leads to the upper bound of new physics beyond breaking scales. This is in sharp contrast to the previous argument. And another interesting example is also the primordial gravitational wave or cosmological tensor perturbation produced during the inflation, because it's proportional to the Hubble scale. Okay. So the non-detection of the primordial density perturbation now gives a constraint on the upper bound of the inflationary scale. Okay. And yet another interesting possibility is so-called the cosmological collider. As I told you before, this tool is very useful to probe physics of the Hubble scale during the inflations. Okay. So the cosmological collider program is very powerful to probe physics with almost fixed Hubble scale because of the inflation. But if you would like to probe the more wider scale of the physics, probably if so-called the genesis scenario was realized instead of inflation, we might have such a chance, but we don't discuss such a possibility. Anyway, as the Hubble parameter gets higher and higher, signal gets larger and larger. This is somehow generic feature in cosmology. Okay. So before going into the detail of the cosmological collider, let me briefly review the generation mechanism of primordial perturbation during inflation. Okay. So maybe all of you know, inflation connects a small scale to large scale, somehow by definition, rapid expansion. And this is exactly the theme of the topic of this session, quantum interplays from large to small scale and back. In case of inflation, just a back. Inflation connects small scales, somehow microscopic scale physics is suddenly expanded to the cosmological scale, like a scale of galaxy or stars. And in such a microscopic scale, quantum effects are very important. And almost immediately it's extended to straight to the cosmological scale. This is first important point. How to generate cosmological primordial perturbation on cosmological scale. Then in such a microscopic scale, uncertainty principle still works or very effective. So this is also schematic figure of the vacuum state of the infraton and the vacuum energy state. And this position is fluctuate due to uncertainty principle. And once we have such a fluctuation coming from the uncertainty principle, this kind of quantum fluctuations are straight to the cosmological scale, thanks to the rapid inflationary expansion, and can become a sheet to produce stars and galaxies. So another question happens: how these field fluctuations transformed into the density fluctuations? Okay. So typically during inflation, only happily the particular scale, the field fluctuates like this way. This is again the schematic figure of the field of excitation value of the infraton and also potential. And this is the history of the energy scale, history of the energy density of the universe. This is the average history of the energy density of the universe. During inflation, it's almost constant, and after inflation ends, it starts to oscillate, and energy density behaves like non-reactive matter, and at some stage, it decays into the standard model particle, and the universe must reheat it, like this way. So, if some point of some field, some region of the universe fluctuates this way, in such a region, history of the energy density behaves like this one. Because to end the inflation, it takes more time. And another later history is the same. And if in some region field fluctuates this way, we have less time to end the inflation, like this one. So at late times, we get the density fluctuations. This is the essential reason why field fluctuations can be converted to the density fluctuation through this mechanism. Okay. So Campagna perturbation or equivalent to the density fluctuation can be estimated to the ratio of this time through the Hubble inverse. And the time is just simply given by the length divided by the velocity. You see? So we can easily get this formula through this argument. Of course, this simple estimate is just applied to the case we consider only the fluctuation of the infraton itself. And if we consider the effect of another field, density perturbation can be more complicated, but from such a density perturbations, we can extract the information of yet another excited field. This is a basic mechanism of the cosmological parameter. As long as we consider only the adiabatic model or infraton fluctuations, this simple argument applies. But once we take into account excitation of another field, such an information is encoded to the primordial density perturbations. And in fact, heavy particles can be excited during inflation. For example, in case of the supergravity or superstring or large extra dimensions, there are a lot of fields whose mass are comparable or even larger than Hubble parameter. If the direction of the infraton suddenly bends like this way, even 3-level heavy particle is excited, or if we have an interaction of the heavy particle through the loop effect, such a heavy field can be excited. And such an excitation can leave imprint on the primordial curvature perturbation, especially if they are non-Gaussian entities. And the first non-Gaussian signature appears in the bispectrum of the perturbation, simply because in Gaussian, bispectrum vanish. And the bispectrum can be characterized by the three lengths of the triangle, thanks to the background homogeneity and isotropy of the background universe. So as long as triangle is equivalent, bispectrum is characterized by just like the triangle. And there are many shapes of the types of the bispectrum, but typically we have two or three typical types of the bispectrum. First one is the so-called equilateral tape. Bispectrum has a peak of this kind of the shape. And in this case, curvature perturbation or density perturbation typically originates from infraton, and the non-Gaussianity is generated at the horizon imprint. And of course, now this non-Gaussianity is strongly constrained by the Planck observations. Yet another interesting one is the so-called local type, squeeze type non-Gaussianity. In this squeeze limits, bispectrum takes a peak. And the curvature perturbation, in this case, curvature perturbation typically originates from another field other than infraton, and the non-Gaussianity is generated during the superhorizon entry. And this non-Gaussianity is also strongly constrained through the Planck subtype. And we have yet another type, but in case of the cosmological collider effect, heavy particle leave imprint on this type of the squeeze type of the non-Gaussianity typically. Somehow this is a quite generic prediction or feature of the cosmological collider. Once we have a presence of the new particle whose mass is larger than half of the 3 Hubble, squeeze limits, we get this simple formulas. First one, we have a oscillatory feature coming from this I is imaginary, you see. And the oscillation can measure the wavelength of the oscillation completely characterized by the mass. So once we observe this kind of oscillation in the squeeze limit of bispectrum, we can identify the mass of the heavy particle. And then this oscillatory feature is somehow represents the quantum interference between infraton and massive particles. I'm going to a bit explain in more detail how this dependence appears. And this 3 half can be understood as the scale of the wave function for the heavy particle. You see, as you know, heavy particle wavelength of the heavy particle decays proportion to the scale factor minus 2 to 3 half. And so this 3 half just comes from such a feature. And this exponential factor, nothing but some Boltzmann separation. Okay. But this formula applies only the single particle case and very simplest features. So more systematic study of the feature of the new particle, like a multiple particle effect, decay, CP phase or something, still need to be investigated. Okay. And this is quite interesting feature of this oscillation. So let me explain how to understand this oscillatory behavior. It just comes from the resonant production and destruction of the heavy particle. In case of the bispectrum, we have a adiabatic mode, light mode. And at some point, we can, through the coupling, either classical or loop, we produce the heavy particle. So at this stage, we get this relation simply coming from equator this part. And of course, to observe the bispectrum of the curvature perturbation light mode, this heavy part must decay into the light mode. So we get the bispectrum, 3-point correlation function. So through this relationship, a wave function of the heavy field is simply take this form, just to characterize the mass. And this time is characterized by this scale factor and the mass. So we get this simple relationship of the to scale of the bispectrum. This is the reason why we get the oscillatory behavior, basically coming from heavy field oscillate, you see, as a wave function. But you might wonder that to observe this signature, mass shouldn't be too heavy compared to Hubble. Because if this mu is too large, Boltzmann separation gets too small or too large, what you see. Too much Boltzmann separation. And also, unless this is order 1, oscillatory feature is typically quite heavy or rapidly, you see. So, to observe this kind of signature, heavy particle, mass of the heavy particle is somewhat fine-tuned to around the Hubble. Because if it's too small, just isocurvature mode, you see, standard isocurvature. So if such a mode doesn't have a baryon number or dark matter, we cannot observe. But if mass is larger than half of the 3h, we have this oscillation feature. But if it's too heavy, too much Boltzmann suppression. So somehow, new particle must have a mass comparable to the Hubble parameter. So it might be regarded as a fine-tuning, but it's not necessarily true. For example, generically, in case of the supergravity, by definition, inflation implies non-zero vacuum excitation, non-zero vacuum, non-zero value of the vacuum, or positive vacuum energy. You see? And such a presence of the positive vacuum energy leads to the Suji breaking. And at least through mediated by gravity, such a Suji breaking effect is mediated to the any particle as an additional soft mass. And it can be easily estimated, such a Suji breaking mass, simply because the Suji breaking effect B times gravity, Newton constant, which is nothing but the Hubble parameter square. So in this context, all of the scalar fields universally receive the Hubble square mass, thanks to the Suji breaking or inflation. So in supergravity, following situation naturally happens, in which there is only light field, only one light field, which can serve as the infraton, and probably protected by the sun, for example, the shift symmetry. And the other fields, you see, most of the other fields can be comparable to the Hubble parameter. So which is very suitable for cosmological collider program. And even if you don't like supergravity or superstring, for example, if we have a non-minimal coupling, like Riemann times pi square, or in general, dimension 6 operator, which naturally lead to the mass of the Hubble. So this might be not so fine-tuned. Okay. And this model was first discussed these people K and 1, and they named called the quasi-singular equation, and later Nima and Joan called the cosmological collider program. Okay. So how to plot mass of the BSL? Okay. So as I told you before, during inflation, except infraton, it's quite natural that all of other fields, like a scalar field, has universally Hubble square mass. And we are interested in, of course, BSL, new physics or new particle. And we are interested in the mass spin or some decay rate or such a feature of the new particle. And but the cosmological collider program, as I explained, probe basically effective mass square during inflation, which is given by Hubble square. Of course, this is quite good in some sense, merit, because otherwise we don't have any signature. You see, if it is too light, just a standard isocurvature. If it is too heavy, just a Boltzmann suppressed. So in this sense, this is quite nice. But some particle physicists may complain. You see, this is not what particle physicists would like to know. Of course, this is quite important and fantastic. You see. But if we say this is cosmological this is collider. So it might be better to plot mass scale of the beyond the standard model physics at current universe, you see, rather than the effective Hubble mass, effective mass whose scale is given by Hubble during the equation. You see. Of course, it's quite fantastic to know first the presence of a new particle in any case. You see. But it could be more fantastic if we know the information of their current mass of the new particle beyond the standard model through this cosmological collider program. You see. And even this case, you see, to know the presence of new particle, please notice that to confirm such a new presence of new particle, we first need to do the estimate of the effect of the standard model particle correctly or precisely. And once we get the signal and extract all of such a effect of the standard model particle, we first claim that we found a new particle. You see. So even if we try to claim the presence of new particle, it's quite complicated or difficult. So in which case can we extract the mass of the heavy particle at the current universe rather than the effective mass? You see. This is the topic I would like to discuss in the remaining time. So I don't claim that this is the solution or this is the unique way. Just one ideal possibility. You see. So for example, if we consider again the supergravity and only consider the canonical K potential like this, which leads to the canonical kinetic time. So in this ideal case, all of the correction coming from the Suzy breaking or inflation universe is universally 3 times Hubble squared. Okay. Please notice that in this simple case. But of course, to be honest, if we have a higher order correction and the coupling, if it depends on the coupling of the particle, we get additional corrections depending on the coupling. And if this lambda I is not universal, not protected by symmetry, of course this correction can depend on the new particle. But let's forget these corrections. Just an ideal case, completely controlled by that. Okay, yeah.
Sorry, I mean, there is a case when the superpotential is linear, then you don't have this. And there is another case when you have a bitter inflation, then you don't have this.
Yeah, sure. I completely agree.
Okay.
I never claim this is the solution or this is the unique solution. Okay. This is one ideal case. I completely agree.
Yeah, in other words, 3 times h squared is absent in those cases.
Yeah, sure. I agree.
So,
I agree.
yeah.
I agree. Completely agree. I never claim this is the solution. Okay. And but you see, if we forget this one, or even if we go to the as Gia proposal, if the equation happens coming from the d term, we don't have this kind of term. Just let's consider the simplest case as the ideal. I completely agree. And this kind of case also happens to be able through the non-minimal couplings. You see, C I square R. And once this coefficient depends on the particle, Hubble correction also depends on the particle. But once we are lucky to have some symmetry or universal coupling, like a conformal coupling, then we get the universal correction of the Hubble sphere. Okay. Anyway, let's consider such a universal case as the ideal case. I never claim this is the solution. And with keeping such a corrections, let's discuss the effect of the multiple heavy particle case, not a single heavy particle. You see, if we have a multiple isocarbon whose mass is comparable to the Hubble, okay, and introduce some coupling, this is a bit technical, so I don't go into the details. But in this case, we found a very interesting feature. Of course, if I and J is the same particle, nothing but just a high frequency mode, completely controlled by this effective mass. But if I and J are different, and then we get a mixing term, we found an interesting feature. Not only just the sum of the mass, you see, which gives the high frequency mode, But also, like a neutrino oscillation, another critical oscillation is controlled by the difference of the mass. You see, low frequency. And so, if we can observe this one, low frequency mode, we get the information of the difference of the mass of the new particle. Not only just the sum of the mass of the new particle, we can get the difference of the mass of the new particle, like a neutrino oscillation. You see, and in some ideal case, as I said before, this is quite degenerate because we simply assume the Hubble collection is a universal. So in this case, we get some information, and this is a little bit schematical figure, but somehow this is the total oscillation behavior, and we can observe just a small modulation on the large wavelengths. So, of course, we have to be very careful, but through this kind of observation of the CMB or bispectral, once we get information that this difference of this mass, we have a chance to probe the mass of the heavy particle in the current universe. Simply because, as I said before, once we have a universal mass, okay, universal Hubble collection, then mu I minus mu j is given by this one. And of course, we need the information of the Hubble. Even if we know this one through that observation, through the bispectrum, we need the information of the Hubble. But if we could detect the primordial gravitational wave generated during inflation, we can identify the Hubble parameter through such observation. So we know this information through the bispectrum, and we know the Hubble parameter from the primordial gravitational wave detection. Then we have a chance to get even the still mass square like a neutrino oscillation, but we have a chance to know the current mass of the new particle. But I completely admit this is quite ideal case. You see, but otherwise, of course, we can know the Hubble parameter or effective mass through the cosmological collider. But again, this might not be what particle physicists would like to know. Okay. So, anyway, yeah, if you are, or especially young people are interested in, we shall discuss how to extract the information of the heavy particle in the current universe, rather than the information of the heavy particle during the inflation. If we really claim that the cosmological collider can be alternative to the collider on Earth, we need such a technique or statistics. Otherwise, this might not be what particle physicists really would like to know. Okay. Of course, you see, if we know the presence of the new particle, it's already fantastic, you see, whatever it is. But if you would like to know the information of the new particle in the current universe, we need more. Okay, so maybe it's not good to go to the introduction. So let me summarize my talk. Unfortunately, at least in the long span, energy scale of collider on Earth is going to saturate, because the radius of the Earth is limited. And so, as an alternative to collider on Earth, cosmology, especially inflation, could be offer another collider, or at least complementary collider. And we, in this talk, we try to address beyond the standard model of particle physics of the current universe, you see, rather than the physics beyond the standard model during the inflation. Cosmological collider originally proposed to probe such a physics or such an energy scale. And this is also quite nice. As I told you before, very naturally during the inflation, all of the heavy particles could have such a Hubble collection. So this is not necessarily fine-tuned, and this is of course pro or merit. On the other hand, this might not be what particle physicists would like to know. This is cons or demerit. So how to compromise this pros and cons? And for this purpose, we have discussed mass spectrum and interactions. And potentially, of course, I admit, my example is too ideal. I never say this is the solution. But if we have such an ideal case, potentially could get useful information, like a neutral negotiation in our case. But just a challenge has just started, so especially young people, if you are interested in, please discuss with me. Thank you very much.
Thank you very much, Masahide. So we have time for questions.
How would these particles affect reheating from inflation? This might.
So this heavy particle typically rapidly decays, so nothing to do with the reheating. Has nothing to do with the reheating. Yeah. Reheating is still coming, of course, in many scenarios, but the simplest one is, of course, inflaton decay into the standard model particle. Because heavy particle typically has a very short lifetime, so it immediately decays. But this is also another interesting topic. How to estimate the decay rate of this heavy particle through cosmological parameter. Some people already tried, but not yet well understood. Yeah, I think this is quite interesting.
Other questions?
This is probably a naive question, but how are you using this during inflation? How are you using the symmetries during inflation? So are you using killing vectors of the...
For example, for this case, I told you that in general, for example, in case of the supergravity, especially the external supergravity, external contributions, all of the particles except the inflation get a half mass in general. But if we import, for example, shift symmetry, phi plus phi conjugate is invariant to what? Phi just to phi plus phi constant, then shift symmetry guarantees the flatness of the potential only in that directions. Of course, this is assumption. That once we impose such a shift symmetry on the inflaton does not receive the happily induced mass. So, yeah, of course, it depends on the situation. And like natural inflation, in some sense, essentially same, just to shift symmetry in the angle.
Yeah, no, yeah, I think my question was actually more on the symmetries of quantity sector, but...
You mean the symmetry of this coefficient?
Maybe we can talk about it later. So.
Okay.
Thanks.
Okay, so, the last one.
I'm curious about your definition of mass. I mean, in current universe, is it a whole mass?
Yeah, of course, we need to take into account the renormalization group effect as well. Sure, I completely agree.
And how about the mass in the inflation? So what is mass in inflation?
So in this case, we need to take into account the standard renormalization group and also the correction from the background of the universe. Both. So yeah, this is quite an interesting point. So normally in the particle physics, just assuming the Minkowski background and depending on the interactions, just runs. But what we would like to know through is that somehow history of the mass during the history of the universe, even taking into account the background universe. So somehow quite interesting to consider such as somehow renormalization. Well, I'm not sure it's good to say renormalization, but the history of the mass during universe. During the history of the universe. We need to invent such a maybe technique as well. Not only simply the renormalization through the coupling, but also if we have a curved background, we get the additional constraint, additional contribution of the mass. Yeah.
Possibly fast.
So there's another interesting effect during inflation that was noticed by Kari Enquist, which is that the standard model Higgs, of course, although it has a zero VEF, also has quantum fluctuations, which means that its variance is substantial, and you can get in non-zero. Is as though the Higgs had a the VEV is non-zero, but its value. The VEV is zero, but its value is non-zero, which gives even masses to standard model particles again during inflation, and these leads to. So we were looking.
Additional mass, yeah.
Yeah. So anyway, that's another
Yes.
interesting effect. Of
Yes,
inflation.
sure. I agree.
Okay, so let's thank our speaker again.
Thank you very much.